This is the fourth and final video for the circuits unit. For this one, let's take a look at a complex circuit. Now, a complex circuit is one that is going to have both series and parallel in it. So, for the AP exam, the largest circuit that you'll be required to do any kind of math with would be a 3 resistor circuit. They may throw a 4th resistor in there, but usually they're going to ask other questions and then they'll have you remove that circuit or that resistor, that 4th resistor, before you have to do any math or anything weird like that. So in this first example, it says that R1 and R2 are in series, because we can kind of see how R1 and R2 are kind of like on the same line. R1 and R3 are in series. We can kind of see how they're in the same line. But R2 and R3 are parallel. So just kind of looking at this, I would say that R1 is in series with R2 and R3, or R2 and R3 are parallel. Now, another word for series sometimes I like to use is in line. And for branch, or for parallel, I like to use branching. Just because sometimes it's not always obvious if two resistors are parallel. Sometimes it's easier to think about them being branching. Here's another example with light bulbs. Now, one thing to keep in mind, the bulb with the greatest power will be the brightest. And remember that when we go to find power, electrical power equals current times voltage. So that's something to keep in mind if you're asked like if you're given a diagram and said something like well, let's take this one. We've got a 9-volt battery, and let's say that each bulb has the same resistance. So let's say that they are 5 ohm resistors, or 5 ohm light bulbs. Which bulb would be the brightest? And just kind of looking at this then, we've got power equals current times voltage, but that's not really too helpful. Remember that voltage equals current times resistance. And if I kind of do some algebra here, I see that power equals current squared times resistance. This is actually a little more useful equation to help us out with this problem. We know that each one has the same resistance, so really it's going to come down to which one gets the greater current. And if you think about it, the amount of current that leaves the battery must return to the battery. But when current reaches a junction, it splits up into smaller parts. So so these two bulbs here that are parallel, this one and this one, which are parallel, each get less current than this first bulb. So that first bulb, since it gets the largest current, this one should be brightest, because it's getting more current, and since power equals current squared times resistance, it's going to be the brightest one. So that's that might be kind of an example problem that you might potentially see on the AP test. You know, if everything being the same, looking at this diagram, which bulb should be the brightest? And for that one, you just look at which one is going to get the most power. All right, now, Kirchhoff's rules. We've kind of gone over them in the last video, but let's just take a second and review. They describe conservation of energy in electrical circuits. So energy changes in simple electrical circuits are conveniently represented in terms of energy change per unit charge through the batteries. That's voltage. Voltage is energy per coulomb. Since electrical potential difference, remember that's voltage, multiplied by charge, and energy is conserved, the sum of the potential differences about the closed loop must add up to be 0. So that was Kirchhoff's first equation. The sum of all voltage drops must equal 0. And what we do is we say that the voltage drop across resistors are negative, the voltage of the battery is positive. The electric potential difference across the resistor is given by the product of the current and the resistance. So that's just V equals IR. The rate at which energy is transferred from a resistor is equal to the product of the electric potential difference across the resistor and the current. So that's just power equals current times voltage. Okay, let's work through a sample problem to get a little bit of math in. So let me draw a circuit here, and you can, if you want to, you can use the back page of your notes for this. So here's my battery. I'm going to say that it's a 9-volt battery. For my closed loop circuit, I have one resistor up here. I'm going to have a junction. Two resistors, another junction for this to return to the battery. I'm going to say that this first one is a 10 ohm resistor, 3 ohm resistor, and a 6 ohm resistor. And what I'd like to find is the voltage drop across each resistor. I want to find the current in each wire, and I want to find the power consumption by each resistor. So those are the 3 things I want to find. The first thing you should do is you should reduce your circuit in order to find the equivalent resistance. So I'm going to redraw this circuit. And what this is going to look like now. So here's my 9-volt battery, my 10 ohm resistor, and I'm going to represent the parallel like this. So this is like my parallel or my branching circuits. So it'd be like 1/3 ohms plus 1/6 ohms, -1, that equals 2. So that 3 ohm and the 6 ohm resistor, when I apply the equation to find the equivalent resistance just between those two, it'd be 1/3 plus 1/6. Invert that, that gives me 2. Alright, now I can think of this as 2 resistors being in series, so to find that equivalent resistance, I can just add those together. So this would be this equivalent resistance be 10 ohms plus this 1/3, which we already know that's 2, so 10 plus 2 equals 12 ohms. So the equivalent resistance of my circuit then is 12 ohms. Now I'm going to use that equivalent resistance to find the total current through my circuit. So the total current will equal the EMF of the battery divided by the equivalent resistance. So that gives me a current of 0.75 amps. So I've got 0.75 amps leaving the battery. That must mean I have 0.75 amps returning to the battery. The voltage then across this equivalent resistor should be 9 volts. You know, if I look at the sum of the voltage drops for this circuit, I got 9 volts as my EMF. I got one resistor which has a potential of 9 volts across it. That gives me my first, the Kirchhoff law. All right, now let's talk about power. Power equals current times voltage. So the current being 0.75 amps, there's a potential difference across that resistor of 9 volts. So the power consumed is 6.75 watts. So I've got 6.75 watts being consumed by that equivalent resistor. Okay, now that we've got that settled, let's move up. Let's start working our way backwards here. So for this one, remember we have 0.75 amps leaving the battery. So because of conservation of charge, I better have 0.75 amps returning to the battery. So that means that wherever I look in the circuit, I should have 0.75 amps. That current should be the same. And remember, current is just a counting game. We're just counting how quickly the charges pass through a point in the wire. Now let's talk about voltages. Ohm's law says that V equals IR. So V equals IR. If I take 10 or 0.75 amps times 10 ohms, I would find that I have a voltage drop of 7.5 volts across this resistor. And then if I did 0.75 amps times 2 ohms, I would find that I have 1.5 volts across that resistor. And again, 7.5 plus 1.5 adds together to give me my 9 volts. So, conservation of energy is still being applied. That's still good. Now let's talk about wattage. P equals I times V. So if I were to take 0.75 times 7.5, I get 5.625. So this 10 ohm resistor is consuming 5.625 watts. And then if I did 1.5 volts times 0.75 volts, I get 1.125 watts. And notice that those two numbers still add together to give me my 6.75, which is good. All right, let's move back up, and now we're ready to analyze our original circuit. So once again, we know that we have 0.75 amps leaving the battery, so we better have 0.75 amps returning to the battery. And that 0.75 amps is going to reach this junction, and then it's going to break up into two smaller currents. Both of those will add up to give me my 0.75. They will then recombine so that I have my 0.75 amps returning. Not a whole lot has happened to this 10 ohm resistor. I still got 7.5 volts across it. It is still consuming 5.625 watts. Oh, sorry, 625. So now let's talk about this branching. Now remember that for branching circuits, the voltage across them will be the same. So since I found 1.5 volts across those, when I combined it to be like a 2 ohm resistor, I still have 1.5 volts across these. That stays the same. And now for the current, I equals V divided by R. So if I do 1.5 divided by 3, that gives me a current of 0.5 amps. And if I do 1.5 divided by 6, that gives me a current of 0.25 amps. And notice that 0.5 plus 2.5 gives me my 0.75. Also notice I have the greater amount of current going to the 3 ohm resistor. That's because it's less resistive, so it's going to get more current. And since it is half as resistive as the 6 ohm, notice that it gets twice the current. So a little bit we can talk about there. Those two currents then are going to recombine at the bottom to go back to the battery as 0.75. Power is current times voltage. So if I do 0.5 times 1.5, I get 0.75 watts being consumed. And then if I do 0.25 times 1.5, I get 0.375. And notice if I were to take that 5.625 watts plus 0.75 watts plus 0.375 watts, they should all add together to give me 6.75 watts. Okay, there's a lot to this one. Make sure you study this circuit over and over and over again if you need to. Something else that you might try to do, make your own circuit. Make it a little different than this one and try to solve it. See if you can find out all those values, all the voltages, all the currents, and all the wattages. All right, that concludes our final video on circuits.